Hey folks, let's continue to go over these test problems. I kind of did this in class and spent a lot of time in class actually doing this, but I'm glad that I did. I think this was useful, kind of having this chance to look over problems and answer questions live. So glad I did it. I'm not going to completely rewrite things though. Let's go by the notes that we took this morning. First problem says, show that if A and B are integers that satisfy A divides B. That's a logical thing, not a actual division. That's not a number. It's a true or false, right? Then show that A to the K, where K is a natural number, divides B to the K. And we did a little work on this. You know, I talk about what you know and what you need to show. And in this problem, we know that we've got A dividing B, which means there's some integer x that allows me to write B as A times x. And I want to show that A to the K divides B to the K. That means that there's some integer n such that B to the K is A to the K times that integer. So it seems pretty clear that if we want to go from here to here, the thing to do is probably use our exponent rules and just raise everything here to powers. B to the K, this to the K would turn into A to the K and X to the K, and that X to the K serves as our integer. So the way we wrote that up nice and clean, we said, okay, since we've got A dividing B, and there exists some X such that it's an integer, and I can write B as A times X. Then for any natural number, I can apply that exponent, K. So B to the K, I'm sorry. Okay, I'm sorry about that. I did have to answer that call. Excuse me. So we're back though. So the way we write that up is we say, okay, fine, here's, since A divides B, then there's some kind of X that's an integer such that B is A times that X. And then for any K, and you could do this with induction, but it's really not necessary because it's not building on the previous step. But for any K, natural number, we have B to the K is A to the X to the K, just raising both sides to the K power. And then this is A to the X times A to the K times X to the K. And then since X to the K is an integer, that means that A to the K divides B to the K. And we're done. Alright. Problem 2 then said, show that for any integer n squared divided by 4 always has remainder 1 or 0. And started kicking around a little bit here on scratch paper just to make sure I believe that. 1 squared is 1, which divided by 4 has remainder 1. 2 squared is 4, which has remainder 0. 3 squared is 9, which has remainder 1 if divided by 4. And 4 squared equals 16, divided by 4 has remainder 0. So not only does it kind of pick between 1 and 0, but it would appear that the odd numbers, when raised to a square, have a remainder of 1, and the evens have a remainder of 0. So it might be a good tip to treat the evens and the odds separately. In fact, it's a great way to generate some 4s, right? If you've got n equal to 2x or 2x plus 1, and you start to square those things, then you get a bunch of 4s, right? So the approach on this one is to let integer n be either, it's got to be either even or odd. So if it's even, then there's an x in the set of integers such that n is equal to 2x. And then so when you square it, you get 4x squared, which is certainly divisible by 4 and has a 0 remainder. Okay. If n is odd, then there's an x such that n is 2x plus 1. But again, when you square that, you get 4x squared plus 4x plus 1. You can factor 4 out. And so by our division algorithm, really, the result of dividing n squared by 4 is the quotient n squared plus x, x squared plus x right in here, and then the remainder of 1. So the only two remainders are 0 and 1. Okay? This one seemed to rough people up a little bit. Show that for natural numbers m and n greater than 1, where n divides m, and we know that a is congruent to b modulo m, that also a is congruent to b modulo n. Okay? So again, this is one where I kind of said, all right, what do you know and what do you have to show? And what do you know is, okay, n divides m, that means we can find an integer such that m is n times x. And then we know that a is congruent to b mod m, that means the difference in a and b is a multiple of m. Okay, so there's exists some k doing this. And so what we want to show is that a is congruent to b modulo n, which means I can take a minus b and write it as n times an integer. But you can do a direct substitution here, right? So let's go back and do that. Since n divides m, there exists an x in an integer such that m is nx. Also, since a is congruent to b mod m, then there exists some other integer, k, such that a minus b is m times that k. And so you could do a direct substitution here, the m for that m, a minus b is equal to m, this is m, so nxk. And since that xk is an integer, then a is congruent to b modulo n. Okay? For problem 4, it asks, okay, take a look at this relation, which is just a set of ordered pairs, and I actually spelled them out for you on the set with elements a, b, and c, and determine if each property holds, if not, explain why. Well, on the set ABC, to be reflexive, you've got to have AA, BB, and CC, and you do have all those things in there. So it is reflexive. Symmetric, though, I don't think so. You've got AC in here, but you don't have CA. Right? And actually, even if it worked, we do have CB in here, and then we do end up getting BC, but it has to work for every point in the set. Okay? And then is R transitive? Well, this is where if we have a condition where I've got A going to C and then C going to B, that I can just go straight from A to B. But in this case, for example, I've got A to C, C to B, but I don't have A to B. Okay. And then lastly in that set, anti-symmetry. It's where you're blinded and no, I'm sorry. Think of something else. It's where you are. If you have a pair that reverse each other, then that means the two things are equal to each other. So we do have, in this case, C related to B and B related to C, but B and C are not equal to each other. Okay. Problem 3 asks now about a relation that we're told is an equivalence class, and we're asked to prove it. So this relation from the integers onto the integers, related if the sum of the squares of the two numbers is even. So for reflexive, we just look at x related to x, and we see that x related to x is x squared plus x squared. That makes that actually divisible by 2, which is going to have to be even. So it is going to be reflexive. Okay. Also symmetric, because it doesn't matter what order you write x squared plus y squared, right? So this happens to be even because of this, and that means this is even, and that means that we get the relation in the other order. Okay? And then transitive, anytime we have x going to y and then y going to z, we should be able to, if it's transitive, to get straight from x to z. So one way to think of this is just even, right? If these things are even, it means that the numbers, the squares, have the same parity. Two things that are even added give you an even. Two things odd added give you an odd. So if these things hold, then x squared plus y squared is even, and y squared plus z squared is even. You could certainly then reason that, well, then x and z have the same parity, and so their sum is even. But if you want to, you can be very explicit and say, okay, there's an m and an n in the set of integers, so that these things are expressed as even numbers. You know, you can say this is 2 times some integer, this is 2 times some integer. Can't be the same integer, by the way. So then solve for x squared and solve for z squared, and then add them. And see what you end up with. It's not really that bad. It's 2 times m plus n minus y squared, which that is an integer, and so we know this is even. That means x is related to z, and that is it. Or, well, not almost. The equivalence classes are for the squares to have the same parity. That means their originals have the same parity as them. You know, the odd numbers have, when you square them, have a square that's odd. And the even numbers, when you square them, have an even square. So all I did here is just solve for x and y, substitute them back in there. Got everybody semi-happy, but mostly convinced them that it was indeed transitive. Okay. Problem 6. It was a function from the lattice points in Z2, Z cross Z, to the lattice points in Z cross Z over here. To do one-to-one, we always do the same thing. Suppose you have two values, and you plug them in the function, you get the same answer. Then what you've got to show is that those two things you plugged in, if you're getting the same answer and it's one-to-one, then that means that the two things you plugged in have to be equal as well. So you can actually solve this. M plus m, m plus 2n equals x plus y, and so forth. But if you solve for n and m, you find out that they're just equal to x and y. And so that means that point we found is the two things we're plugging in are equal, and that means it's we've proven that f is one-to-one. Okay. And likewise on onto, what you can do is just pick a point in Z2, the destination space, and then just reverse calculate what things would you have to plug in to get AB. That's kind of what it looks like. You got a lot of cancellations. Okay. And then problem 7 was actually pretty quick. Let's see if I can find the little notes that I wrote on this one. Yeah, here we were kind of doing the know and show business. I know that to show that the composition is one-to-one, I have to start with 2 points, show that they, and let them be equal to each other, and then show that that forces then the things plugged in to be equal. So here's a sub 1, here's a sub 2 in there, and then this part and this part are in there, which means since G is one-to-one, that means f of A1 equals f of A2, which f is one-to-one, and that means that a sub 1 equals a sub 2. Okay, and that's what we have to show. So let's actually write those steps down. Suppose you've got this happening with two different things. I didn't say they were different, but two things here with different labels. and then we look at g of f of a, whatever it is, we see that these two things are, since f is equal, is 1 to 1, and that that then forces, since f is 1 to 1, that a sub 1 equals a sub 2. And that's all you need to do to show that it's 1 to 1. Okay? And then as far as the last one, anytime we're going to show that a set is a subset of another one, chances are we just take a random element, pitch it in the mix, and just see where it has to land. So in this particular one, I just let A be something here in X, which is a subset of A. That means there's some B that it maps to, and that means if AB is in this, then BA is in that. And that means that when we look at the composition, we've got, starting with F, A to B and B to A. I got that. Okay? And particularly the fact that it lands over here in the image means that, okay, this thing that I started with on the left-hand side is actually part of the right-hand side too. Okay? And then the only other thing is the counterexample, and I hinted at this, suppose you've got set A with two things in it, set B with one thing in it, and let's say that maybe your subset of A that we're going to fool with is X. And let's say that the function we're dealing with matches everything to a ducky, okay, an Easter ducky. Then when they go to look at f of X, well, it probably won't tell them that because it's not a calculation, it's a set. But it is a set that is a pet. It's my chicken. So everything in X, the 1, gets mapped to the chicken here. And then when you look at everything it gets mapped to the chicken in general, well, everything does, right? 1, 2, okay? And so there's a case where the image is not a subset of X. Okay? All right, I will stop there. That's the test, and I will soon have some lecture notes for a little bit more material for you. We've got problems to work from today that we didn't get to, but also a little bit more that I want to do with you. So I will call it a stop right here. And got to get sorry, that's what I'm looking for.